Dear colleagues, first let me wish you a nice day. My name is Slobodanka Boljanović, Research Associate Professor, and I'm coming from the Mathematical Institute of the Serbian Academy of Sciences and Arts, Belgrade, Serbia. Please note that this research work is the result of my collaboration with Professor Andrea Carpinteri from the Faculty of Civil Engineering, University of Parma, Italy. Let me start with my presentation with title Fatigue Degradation Analysis of Elliptical Damage. Sustainability, according to the damage tolerance philosophy, requires the protection of large moving systems from any kind of deterioration over their life cycle. However, sudden localized surface damages, defects due to complex loading profiles can seriously threaten the spent vessels during exploitation. Therefore, in order to prevent fatigue degradation, it is important to establish efficient computational frameworks that enable reliable durability assessments. The main research goal of this work is to develop the fatigue design strategy for assessing the failure strength of plate-type configurations with crack-like elliptical flow. Here are points that will be considered in my presentation. Fatigue analysis for the plate with quadrilateral corner crack in terms of residual life calculation and crack path simulation. Driving force evaluation along the crack growth front using fracture mechanics-based analytical model. Effects of loading geometrical parameters on the component life, cycle loading, constant amplitude, and implementations of proposed computational framework. The detrimental effects of microconcentrators caused by stress gradient in the zones with initial flows can be avoided during service operations if such safety-relevant mechanism is explored through suitable fracture mechanics concepts. Thus, the fatigue degradation analysis should be performed in terms of crack growth rate as a function of the stress intensity factor. The propagation of part-through corner crack is herein tackled through crack growth rates in depth and surface directions using two different fracture mechanics models. First one expressed by equation 2a and 2b, and the other one given by equation 3a and 3b, where delta Ka and delta Kb are stress intensity factors in depth and surface directions. dA, dN, and dB, dN are the crack growth rates for mentioned two critical directions. Ca, Cb, Ma, and B are material parameters experimentally obtained. Through the fatigue endurance design, the number of loading cycles to failure is evaluated by integrating the crack growth rate for relevant initial A0, B0 and final AF, BF crack growth length in depth and surface directions. In this context, number of loading cycles expressed by equation 4a and 4b is obtained using equation 2a and 2b, whereas equation 5a and 5b are obtained after integration equation 3a and 3b. Bearing capacity of structural components with damage may be often threatened due to a complex interaction between surface loadings and environment. Such effect is evaluated through fracture mechanics parameter M given by equation 6, which was involved in 1 MOA concept. A complex singular stress state field is responsible for the occurrence of fracture due to accumulation of damage in the vicinity of the crack tip. From fracture mechanics point of view, such driving mode zone should be considered either in terms of stresses or displacements expressed by equation 1a to 1c and equations 2a and 2b, where stresses, displacements are tackled as relevant functions of the stress intensity factor. The quantification of disturbed stress field in safety critical zones in terms of system durability requires tackling the effects of stress razors associated with service loadings via stress intensity factor using analytical and or numerical fracture mechanics models. In general, the stress intensity factor in the case of elliptical crack can be evaluated for depth and surface directions using equation 7 and equation 8, where delta S is applied stress range, A represents crack length, and FCOR-A and FCOR-B are relevant corrective functions related to the shape of elliptical crack. According to fracture mechanics, the fatigue behavior of quadrilateral corner crack is explored employing equation 9, where delta S and A are applied stress range and crack plan, delta K is the stress intensity range, and Q represents the ellipse-shaped vector. Crack shape variations under cycle loading are theoretically analyzed using the corrective factor FQEC expressed by equation 10. Failure mode due to quadrilateral crack is evaluated combine the effects of crack size, crack shape, front face, and thickness of the plate through relevant corrective factors M1, M2, M3, G1, G2, Fv, shown after equation 10. Fracture mechanics-based computational framework generated within this research work is presented in figure 3. For the failure evaluations of plate type configurations, geometrical and loading parameters associated with material properties are used to explore the stress intensities along the crack front under cycle loading. Then, by employing two-parameter driving force concepts, the crack growth rate is generated. Further, the residual strength was assessed in terms of number of loading cycles. Moreover, driving moment progression was analyzed through the crack path evaluations. Now, some applications will be considered in order to assess the predictive capability of developed fatigue design model. Firstly, the failure strength of the dog bone plate with quadrilateral corner crack shown in figure 7 was evaluated in the case of 4 different levels of applied stresses with 2 different stress ratios, R equal to 0 and R equal -1. Relevant loading conditions, geometrical parameters, and material properties are shown on the left side of this slide. Fatigue-induced plate failure is herein assessed combining equation 4a and 4b and set of relationships for the stress intensity factors, equation 9 and 10, associated with relevant parameters factors M1, M2, M3, G1, G2, Fp. Since the residual leaves for the same configuration were previously evaluated by the present authors, reference 2, through crack growth concept given by equation 3a and 3b, they are also involved. Relevant theoretical outcomes reported in reference 2 are shown in figure 5a and 5b, whereas those obtained through this research work are plotted in figure 5c and 5d and in table 1 shown on the next slide. Note that figure 5a and 5c represent life versus crack length in that direction, and figure 5b and 5d are those related to the crack length in surface direction. In the case of maximum stress equal to 342 megapascals and stress ratio equal to 0. Now, in the case of maximum stress equal to 273 megapascals and R equal to 0, evaluated number of loading cycles as a function of crack length in depth direction and surface direction are shown in the table 1, figure 6a, 6c, and figure 6b, 6d, where estimates shown in figure 6a and 6b are from reference 2, and those plotted in figure 6c and 6d are the present results. From comparison shown in table 1, it can be concluded that fatigue estimates obtained through the computational framework developed within reference 2 are more conservative with respect to experimental data from reference 1 than those generated through framework proposed in the present research in the case of stress ratio equal to 0. Through damage tolerance-based analysis, the residual life was assessed in the case of cycle loading with stress ratio equal to -1. Fatigue outcomes for maximum stress equal to 310 megapascals are shown in figure 7, where estimates plotted in figures 7a and 7b are from reference to, and those shown in figure 7c, 7d are the present results. Now, evaluated residual leaves under cycle loading with stress ratio equal -1 are compared with the experimental data reported in reference 1 as is shown in table 2. Moreover, the number of loading cycles as a functions of crack length in depth and surface directions are plotted in figure 8a, 8b and figure 8c, 8d, where estimates shown in figure 8a and 8b are from reference 2, and those considered in figure 8c and 8d are the present results. From figure 8 in table 2, it can be concluded that fatigue estimates obtained from the present research work are more conservative with respect to experimental data from reference 1 than theoretical outcomes generated in reference 2. Through the fatigue evaluations herein presented for the plate with elliptical corner crack, figure 9, the effects of stress ratio and thickness are analyzed under cycle loading. Relevant geometrical loading and material parameters are shown on the left side of this slide for the plates subjected to 3 different stress ratios and in the case of plates with 3 different thicknesses. All plates are made of aluminum alloy 2024 T3. The evaluated number of loading cycles as a function of crack length in depth and surface directions for 3 different values of stress ratio are shown in figure 10a and 10b. Further, fatigue estimates obtained in the case of 3 different thicknesses are plotted in figure 10c and 10d with respect to crack length in depth and surface directions. Relevant comparisons shown in figure 10 indicate that stress ratio and plate thickness may have significant impact on the residual strength of plate type configurations with elliptical crack. Through the driving mode analysis under cycle loading, the effect of applied stress is explored. Thus, by adopting geometrical loading parameters and material properties shown on the left side of this slide, the residual life was assessed in the case of 3 different values of maximum forces, using equation 4a and 4b and equation 9 and 10 coupled with relevant stress intensity parameters M1, M2, M3, G1, G2, F3. Evaluated number of loading cycles as a function of crack length is shown in figure 12, where figure 12a represents life versus crack length in depth direction and figure 12b shows life versus crack length in surface direction. The plate failure under cycle loading is herein explored through the crack path evaluations. Fatigue parameters related to the loading conditions, geometry of the plate shown in figure 13, and material properties are listed on the left side of this slide. Damage tolerance-based fatigue design herein presented involves the crack path analysis by employing equation 2a and 2b and equation 9 and 10, associated with relevant stress intensity parameters. Evaluated crack paths are shown in figure 14a and 14b for 8 different crack lengths in depth direction, where vertical and horizontal axis matches with front face and left edge of the plate, and initial crack is characterized by A0 equal 1.6 mm and B0 equal 2.2 mm with respect to depth and surface crack growth directions. Demands to assess the durability performance of modern large moving systems are raised to avoid the sudden losses of their resources due to detrimental effects of manufacturing environmental flows under service loadings. Therefore, this research work proposes damage tolerance-based framework to analyze severity of such crack-like stress razors by taking into account the effect of stress ratio. Novel expressions successfully experimentally verified generate the changes in the fatigue response, providing correlation of the stress intensity variations as well as the residual life with respect to crack length in depth and surface directions. An important benefit of the analytical framework presented is that it can assess the failure strength under cycle loading simultaneously through residual life of component and crack growth path.